Okay, so what you're going to get are two different videos. The first one, they're both pretty short. The first one is covering the electric field, and the second one covers electric potential and electric potential energy. I think the electric field is a little easier to kind of understand since we've already done gravitational field, so we'll start with that one. So, electric field. A charged particle exerts a force on particles around it, and you know that because we did Coulomb's law, and you remember Coulomb's law was F equals K, which is Coulomb's constant. Pretend that's an arrow. All right, let me calibrate my board. Hold on. All right, we'll try that. So K, if you remember, is Coulomb's constant. And the value for that was 9 times 10 to the ninth. It's a very large number. But that means that any Q exerts a force on any other Q that's separated by some distance r. That's all that means. Just like M1, M2, and universal gravitation. It says we can call the influence of this force on surroundings as electric field, just like a gravitational field. It can also be stated as electric force per charge. Electric field is represented with a capital E, and Newton per Coulomb is the unit. There's no clever unit for this like joules or anything. It is really just a Newton per Coulomb, or the unit of force acting on a unit of charge. It is a vector, so it does have a direction. And just like gravity, if you remember before, gravity would decrease at an inverse square. So as you got farther and farther away, it would decrease by a square function. Same thing here. So that's good news that most of the deal about the electric field you already know. Once again, the big difference is electric fields can attract or repel. So if you look over here, you see the equation is E is equal to F over Q. Actually, and if you look, F is just K Q1 Q2 over R squared. Well, if you take that whole term and you divide by Q, you lose a Q out of it, and what you're left with is K, which is still Coulomb's constant, Q over R squared. And once again, the units are just going to be newtons per Coulomb. So you will have it on your equation sheet both as this and as this. There are a couple little notes about the electric field. You cannot see the electric field, but you can observe the effects of it. That's the only way that we humans can see the electric field, isn't by looking at it, but looking at what it does, just like you can't see gravity, but you can see what it does. To find the electric field vector of a point charge, we assume that it is a +1 unit. So this is how it's notated. You have a charge. Let's make it easy. We'll make it a positive charge. Now we need to draw the field. Now we can't see this, but we still need to find a way to visually represent it. So what we do is we draw vectors. It is common to draw 8 vectors per charge. That is not the absolute rule. If you drew 6, that would be fine. If you drew 20, I'm sure they wouldn't mind that either. But usually there's 8 lines per Q. Now, if I want to find out what the electric field is, so now I have this electric field drawn. If I want to find out what the field is right here, what I do is I insert something called a positive test charge. A positive test charge has a value that is positive, but it's not a real value, because if I put an actual plus charge in here, that would change the field. These lines would bend away because plus hates plus. So we insert a positive test charge that does not affect the actual field that you're putting it into. And if, for instance, you want to find the electric field due to 2 charges, then you simply find each one individually and then add them up. So that's something we have also done before. So these are basic electric field lines. You can see that the field lines come out of the positive because, once again, we want to know what the effect is on a positive charge. And if I put a positive charge right there, you know that it would be pushed in that direction. And that's all the electric field is. I know that right here, a positive charge would be pushed in that direction. I know that right here, a positive charge would be pushed in that direction. So that's all the electric field is. It's just an infinite amount of points of what would happen to a positive test charge. Likewise, around a minus, if you put a positive charge here, I know it would be pulled in towards the negative. Positive charge here, I know it would be pulled in. So field lines go into positives and they come out of minuses. Also, if you look at your field lines, where they are the most dense, aka where there are the most amount of lines, like in these areas, that is where the field is the strongest. And that makes sense because when you look at this, you know that F equals K Q over R squared. Well, if I bring a Q even closer and closer and closer and closer, that makes my R go down. And this is an R square value. So if you look at a field line diagram, where the lines are most dense, aka there's the most lines, that is the strongest field. Another couple hints about field lines. So if I have an electric field, let's say here's a plus, and I'll draw a minus over here. Remember, there's 8 lines, so 1, 2, 3, 4, 5, 6, 7, 8, equidistant. These lines need to leave perpendicular. You will never have a field line that leaves like this or like this. They have to leave perpendicular. Now this is another single charge, so it will allow 8 lines to come in. And now we just look. I know, and I'm going to put my finger right here, I know that if I release a plus charge, it is going to travel in that path. A little positive test charge would move towards the negative. This one would be repelled, and then it would come back in. Repelled, and then come towards the negative. Repelled, and then eventually come towards the negative. And you can kind of see the pattern that's going to happen here. If you're ever drawing these and they go off the paper, that's fine. Just bring them back on. Now this line, that last line, I drew the horizontal one, this one right here. I kind of picture like coming out of the paper, around, and then back into the paper there. It's just easy for me to visualize that way. You'll also notice that these field lines never ever intercept. So they leave perpendicular, they enter perpendicular, and they never cross. Because if I had a field line that somehow came in like this, that means at this point right here, I've got 2 electric fields. You can't have 2 electric fields at one point. So the field lines will never cross. A very, very quick example. It says find the electric field created by the charges A and B at point C in terms of K, Q, and D squared. You'll find that D and R squared are kind of interchangeable, but just to make life easy, let's use R squared. So I need to find the field at point P. Well, the field at point P is affected by both this charge and this charge. And how you do this is just like we've done with vectors since almost the first day you came in. You find the force for one, you find the force for the other, and then you simply take the vector product of that. So, drawing our field lines, because of charge B, I know there is going to be a field to my left, because this is a minus. And remember, we always choose a positive test charge. So C, even though it doesn't have an actual value, is positive. It will be attracted to B because B is negative, and it will be repelled from A because A is positive. And now you simply solve for each one. So insert the picture here, and now if you look, A is a value of 4q, and it is a distance of 2d squared. Well, 2d squared is, the whole thing is squared here, so if you look at it, the whole thing is squared, and this was a 2, so now it becomes a 4 times d squared, and we're using r. For b, it is a distance of 1d away, so 1 squared times d squared is just d squared. And then you plug in the -2, it comes along with it. In order to find the total electric field at any one point, you just take A plus B, and that should give it to you. Now, if you look, remember that they were moving in different directions, so we have to subtract them, and that's why it's minus right here. Okay, so once you're done solving it out, my 4 is canceled out here. I left me with Q over D squared. Over here, nothing canceled out, -2, that all stays there. You notice the negative comes down here. So now I have Q and everything, and it works out to that final answer. So electric fields really aren't too difficult as long as you're careful and you just pay attention.